and that particularly is relating to the homework due tonight. So basic transfer function taking up this information in the system dynamics basically is expressed in terms of concept transfer functions. Okay, the transfer function is such that by definition is G is equal to the output related to the input, or vice versa, the output equal to G multiplied with input. Okay, so how to get a transfer function? This is our dynamics. We simply take a Laplace transform without considering initial conditions. So basically, this dynamic system second order degrees, and that can be replaced by this. Okay, and the easiest way to see is you simply replace the double derivative with a square and vice versa. Okay, for no derivative, you simply replace by 1. And then this is the input, this is the output. You put into the relation between output and input ratio, that you can get the transfer function. Actually, this transfer function is 1 divided by this polynomial. Okay. And how to calculate transfer functions? And in terms of frequency domain, we simply replace S equal to J omega. Okay, and then for quantity equal to J omega, then transfer function can become complex functions. Okay. Complex functions compared to a complex number, the complex number always can be represented by a magnitude and multiply exponential of his phase angle. Okay, that's a different expression. We're going to adopt this expression, basically magnitude multiplied with the phase angle. So in the similar way, the functions also can be represented by the magnitude, which again is a function of omega. And again, multiply with this phase angle, and again, that's a function of omega. But you compare this function with a constant, basically they have the same patterns. Okay, so that's the easiest way to see this one. Then we look into a little bit more details how to calculate this one. Again, we starting from here, you take the Laplace transform, and from there you can get the ratio between output to input. Then you can write it down this transfer function correctly, and then we replace the S equal to J omega. Okay, so basically with these functions really we put into here. So basically right now we are working as the complex function here, and for the complex function, the first one you organize the real part, and then you organize the imaginary part separately. Okay, so with these things, then we can try to calculate its magnitude. The magnitude basically equal to this, okay, and the phase angle equal to this one. Basically, the phase angle is arctangent of real part and divided by the imaginary part there. Okay, so that is the calculations. And
imaginary part divided by real part.
The imaginary part by real part. Okay, and so that again, that is a process, and in this page you can compare with the numbers here. Okay, so for this number, maybe I can try it one more time. So for these transfer functions here, we are working with is starting from here, that is q minus omega squared and plus j times q omega. Okay, so let's work on these complex numbers, the functions. So basically this one is equal to, on the denominators, it has a magnitude 1, and it has the phase angle. So basically for the phase angle is 0, okay? And for this one has this is the real part, imaginary part, so its magnitude equal to the real part square and plus the imaginary part square. So that is 2 minus omega square, and this is 2 omega. Okay, so that's the magnitude. And the phase angle basically is, let me using theta. So theta equal to arctangent. Arctangent right now in the denominator here, that is arctangent of the imaginary part divided by the real part. Okay, so we have this one. And right now we continue. So now here is the division of the two complex numbers. And right now the complex number has been represented in terms of magnitude with the phase angle. So doing the division is pretty straightforward. Simply in terms of magnitude, they simply divide by themselves. Okay. In terms of the phase angle, simply is the subtractions of the numerator. Subtraction of the numerator divide from subtraction of the theta from 0. So basically that is this one. Okay, so that is become this and then minus theta. Okay, so if really want to get into compression in the formal way, so that is exponent and arctangent. So you simply put it arctangent here. Good. Any questions? So there's a minus. Okay, so that is on this slide here. And the MATLAB help us to plot this kind of the magnitude and phase angle pretty easily. And here, let me introduce this command. So again, the first one you arrange into the transfer functions. So if you remember, for our transfer functions, basically is 1 s squared plus 2s plus 2. Okay. So in MATLAB, the transfer function is such that you define your numerators, which is placing the coefficient in the descending order of s. And then the denominators, again, you place the coefficients and 1, 2, 2 in the descending order in s. Okay, and then you define your transfer functions. Your transfer function is simply say systems equal to TF, and NUM, DEN. Okay, then that is the transfer function here. So basically we're using TF, and here I define it as G. Okay, so basically that the name I give is G here. Okay. So once you define your transfer function, you're simply using this command body, BODE. Okay, you put the transfer functions description into the body, then in the MATLAB it will give you two plots. And one is about the magnitude, one is about the phase angle. And then that is ranging in certain default omega, or otherwise you can put your omega range here as well. So you can look up help body, and that will give you how to correctly use this command. So this is the quickest way to use this one. And so from here you can graphically to learn how to define the bandwidth, etc. So the kind of the old information, kind of definition for bandwidth or for the Q factors, those things can be used here. Okay. So this is another different system. So you can see this curve is look more familiar with to us Q factors or the multiplication factors. Okay, something like this one here. Okay. So this page basically to summarize what we have learned in the time domain, which means at the very beginning of this chapter 3, we solve directly in the differential equations. Then we have such expression. We assume the steady state or non-homogeneous solution is in this form. Then we know we are able to calculate capital X equal to that one. Okay, and then phase angle is something like this. Okay, and using the Laplace transform and the transfer functions, again, we can have the same result. And so x of s equal to next page here. So this one, again, this work is about the calculation of the transfer function, and the system is this. The time domain is like this. In the transfer functions, we already determined the transfer functions like this. Then we know the input. We want to determine the output. Output magnitude simply is multiplication of the input with this. Okay, F now times M omega. That gives us the output magnitude. And for the output, the angle here, I forgot to change it. Let me change it directly here. So again, the magnitude of the output equal to the magnitude of the transfer function with the input. The angle, the phase angle simply is the additions because they multiply together getting to the output. So the phase angle must be added up together, omega t plus this angle here. Okay, so that is the form. So we simply plug in, we've been calculated the magnitude of the transfer function, and then we plug in the phase angle of the transfer functions. Okay, so like this one. So basically, we'll plug in here, then you can get the same result as we have in the time domain. So this page basically summarizes what we have learned using the transfer functions compared to the time domain. And this page is important. Basically, if you like, you can use this one as your cheat sheet. Okay, basically this page summarizes everything we learned on the theory of the. Okay. So that is about the transfer functions. So good.